Welcome to Summarize Science. Today, we are diving into a fascinating breakthrough in quantum state preparation. Quantum computers rely on preparing very specific patterns of information called quantum states. One of the most important patterns is the Dicke state, which is like a uniform team where a specific number of members are active at once. These states are vital for quantum metrology, which is the science of making ultra-precise measurements of things like gravity or time. However, creating these states is usually very slow and requires many steps as the number of qubits increases. Previously, scientists thought they needed a specialized operation called fan-out to make this process fast. Fan-out is like a megaphone that instantly copies a single piece of information to every part of the computer. This paper presents a way to create these states in what is called constant depth. This means the number of steps stays the same even as the system grows much larger. This is a massive win for efficiency on today's noisy quantum hardware. The researchers developed a clever strategy using buckets to manage the complexity of the qubits. By partitioning the system into smaller groups, they can build up the overall state more reliably. One of the biggest hurdles was figuring out how to include all the strings of information that usually get lost in simpler methods. They used a mathematical trick to add back the missing pieces without slowing down the entire process. They also utilized a technique called amplitude amplification. This is essentially like turning up the volume on the correct answers while silencing the background noise. This ensures that the final quantum state is exactly what the scientists intended to create. Interestingly, this method works for all symmetric states. These are states that look the same even if you swap the positions of the individual qubits. This makes the discovery broadly applicable to many different types of quantum algorithms. The paper proves that you do not actually need the high-powered fan-out gate for a wide range of these states. This is surprising because it suggests that simpler quantum hardware might be more capable than we previously realized. By proving these new upper bounds, the researchers have closed a major gap in our understanding of quantum circuit complexity. It provides a roadmap for building complex, entangled resources on real-world machines, like those using trapped ions. In summary, this research simplifies the recipe for building essential quantum components. In the future, this could lead to faster quantum sensors and more powerful simulations of chemistry. This breakthrough shows that constant depth circuits are more powerful than many experts expected. Thanks for watching Summarize Science.